right?
Yes, I'm here.
Okay. Okay.
Let me share my screen.
Yeah, very happy. We're very glad to invite Zhicheng here to give an invite talk. Zhicheng right now is a staff research scientist at Facebook Research. His invited talk title will be Decoupling Representation and Classifier for Long-Tailed Recognition. Dr. Zhicheng, his work focuses on building large-scale image and video understanding platform. His research interests mainly include computer vision and machine learning. He received his PhD degree from Department of Computer Science, UIUC in 2016. Okay, let's welcome Zhicheng for his talk. Thanks. I think Zhicheng, you can start. Thank you.
Thanks for the introduction. First of all, can you guys see the slides?
Yes, I can see the slide.
Cool. Okay, I'll move on. And thank Li Wei for the introduction. So it's a pleasure to join the workshop. I think it's focusing on important problem in the community. And as the previous presenter pointed out, in the real world, the data set is usually long-tailed distribution. So I'm happy to present our recent work in ICLEA 2020 and on the topic of decoupling the representation and classifier learning for long-tailed recognition. This work is a joint collaboration between Facebook AI and the National University of Singapore. So as Bo-Qing pointed out, so in the real world, we are not facing a class-balanced data set. So in the real world, data set is usually long-tail distribution. So we have the header classes with many more training examples than the tail classes. And then we usually divide the classes into 3 categories. There are many shorter classes, which has the most number of the training example. We have the media short classes, which has a moderate number of training examples. And we also have the most difficult few short classes where the training examples is really rare. And in the test sets for evaluation purpose, we have the balanced distribution. So which means we want to achieve high performance over all the classes rather than just focusing on the header classes only. So existing methods basically taking 2 approaches to solving this problem. They either rebalance the data set or rebalance the loss during the training. To rebalance the data set, you can upsample in the tail classes or you can downsample in the header classes. To rebalance the loss, you can actually assign large weights to the tail classes or you can assign smaller weights to the header classes. And those methods has improved the baseline results. However, we find that there's a problem, that is, those methods actually tightly couple 2 things together. One is the feature representation learning, which is usually achieved by the backbone model, and also the classifier training. So in our case, it could be as simple as a linear classifier. Our hypothesis is the final classification performance depends on both the quality of the representation and the classifier. So in the baseline training, where you don't rebalance the set, where you don't rebalance the loss, you actually get a good representation learned from the data. However, since the data set is long-tailed, the classifier quality is suboptimal. So the overall performance is mediocre. So previous method tried to resample data set. And by doing this, you actually compromise the quality of the representation while you are improving the classifier a lot. So the overall performance is still improved, but we think we can do better. So in this project, we decouple the representation learning from the classifier training. And then we show in this work by a bunch of experiments on the benchmark showing decoupling the representation learning and the classifier training, we can actually improve the results 1 step more. And our results are mostly drawn from empirical studies by evaluating on 3 benchmarks. So here is the basic notation used in this project. We assume we are taking the image as input by going through the backbone model, such as with net, you can extract a feature representation. And the feature will go through the linear classifier, which give you the classification logic. And your final prediction of the class is the class with the largest classification logic. So that is the simple baseline setup in this work. So what's the problem in the baseline training? So we actually run experiments. We jointly train the ResNext 15 model along with the linear classifier using the joint training in a single stage. After training, we visualize the norm of the weights of the linear classifier, and then we find actually there's strong correlation between the norm of the weights and the size of the classes. So basically, those head classes have many more training examples, and their weights have larger norm compared with the tail classes. So we see this is a problem in the classifier, which will bias towards those head classes during the classification. Those tail classes will have pretty small weights in the classifier, so consequently, it will give very small confidence score. And eventually, the final classification will have pretty poor performance on those tail classes. So how can we solve it? Our basic idea is straightforward. So we want to break such correlation between the weight norm and the class size. We want to have more evenly distributed weight norm across different classes. So we try a bunch of different ways to achieve this goal. So here, there are 3 things that work in practice. First, you can actually retrain the classifier. Say you train the backbone and the linear classifier in the first stage, end to end. And in the second stage, you can freeze the backbone, which means you freeze the representation. And we simply retrain the linear classifier with class balanced sampling. So you basically sample more examples from the tail classes. So by doing this, we can also visualize the norm distribution. And we find this time, the norm distribution is actually more even and balanced than in the case baseline. The second way we tried out is more straightforward. So we simply normalize the classifier weights, and we introduce a simple hyperparameter, temperature, tau. So it's actually regulating the normalization. If you set the tau to be 1, so that is the vanilla L2 normalization. And if you set tau to 0, you basically keep the normal, the weights not change. So in practice, we empirically choose a value from 0 to 1 in this setup. So by doing this, you can achieve similar results. The distribution of the weight norm is more balanced than in the baseline. The third method is one step further, so we can actually run this tau hyperparameter from data. So the way we do it is after the first stage, joint training, we can actually freeze the trunk, freeze the linear classifier, and we use class balance sampling to learn this tau using the cross entropy loss. Since the number parameter is very small, it's basically 1 tau per class, and the optimization is an easy task. And the results shows we can always also balance the distribution of the weight norm by doing this learnable weight scaling. So we actually study different combination of the data sampling and the classifier rebalancing. So if you focus on the baseline setup, where you only have one stage, use the joint training of the backbone and the classifier, and you actually can have different data sampling strategies. So the baseline would be the instance balanced way. And we also try different ways. For example, we can have class balanced sampling. We also propose a progressively balanced sampling, which means during the entire course of the training, you progressively shift from instance balanced sampling towards the class balanced sampling. So if you only have one stage during training, we find the overall performance is best when you use the progressively balanced sampling. So this is something people didn't try out before. I think people try to have two-stage training. You start with instance balance, then you switch to class balance before. But here we show actually by smoothing out this kind of transition in the sampling strategy, you can squeeze a little bit more gain on the overall performance. So the second finding from these experiments is if we can allow to rebalance the classifier, so what's the best combination in terms of sampling strategy and the rebalance method? So we found in this study on this ImageNet long-tailed data set, the best performance is achieved when you use instance balanced sampling in the stage 1, where you want to learn a pretty good representation of the feature. And when you rebalance the data set, when you rebalance the classifier, you actually have multiple choice. So we tried out retraining the classifier, and we also tried out simple TOR-based normalization. These two methods is actually working equally well and much better than the baseline methods. And we can see, especially for those media shorts and a few short classes, by rebalancing the classifier, the performance on these two categories of classes significantly increase, while the drop of the performance on the many short classes is minimal. So the overall performance is actually much, much better than the baseline single stage joint training. So this is really interesting findings in this paper. And how does the classifier rebalancing work in this way? It sounds like very simple. So we think this is related to the decision boundary in the feature space. If you don't normalize weights, those weights have different norm, and the header classes has larger norm for their weights. And as visualized in the plot, we think the decision boundary is biased towards the header classes. Those header classes will have wider classification coin in the feature space. So it's more likely to be predicted. And to balance such decision boundaries, by normalizing the weights using a tau hyperparameter, we can actually make the decision boundaries more balanced in this case. So that's achieve the effect. We can improve performance on those media shorts and a few short classes. The next question would be, can we fine-tune both the trunk and the classifier after stage 1 of the joint training? That is something possible. We actually run experiments on ImageNet long-tail this data set as well. So once we finish the stage 1 training, we learned backbone model, we learned linear classifier. We actually can fine-tune it using different sampling, for example, class balanced sampling. We find if you fine-tune both the backbone and the classifier, the performance can improve in terms of overall performance, also performance on the few short classes. However, the best shot we find is you actually can freeze the backbone, freeze the representation. If you simply retrain the classifier, and you can actually get the best performance. We hypothesize the feature representation is best learned by instance-based sampling, where you actually don't alter the sampling, you respect the natural distribution. So here I'm going to present some results on 3 data sets. I think first data set is actually from the paper previous presenter talked about. It's a subset of ImageNet. It's 1,000 categories as well, but the distribution is highly skewed. And we also evaluate on the iNaturalist. And also the place long tail dataset is also created from the original places dataset. So the ImageNet long tail dataset is highly imbalanced in the class distribution. So the head classes can have more than 1,000 classes, where the tail classes only have fewer than 100 classes. So this is creating a lot of difficulty to achieve high performance on those tail classes. First, we compare our method with the baseline, which is the joint training, where you only train once, you train both the backbone and linear classifier end-to-end way. So we find actually you can easily improve performance on those media short and the few short classes by doing a class rebalance. You can do it through the classifier retraining. You can normalize the weights after the joint training, or you can learn the tau in the normalization by having additional fine tuning in a second stage. And we found that the performance improvement on those media short and the few short is a lot. We found empirically you can get 10% improvement on the media short classes and over 20% on the few short classes. So you get a little drop on the head classes. It's usually few 4%, but when you average over all the classes, the overall performance is still improved significantly. So we think the class rebalancing is a really easy way to improve performance on those tail classes. And the learning, like retraining the classifier or just picking a reasonable value of the tau is relatively easy and small optimization compared where you learn the backbone model jointly with the classifier. So the iNaturalist dataset is way more challenging in the sense, first, it's a realistic dataset collected by the professional. It has over 8,000 categories, and natural distribution is highly imbalanced. So previous work also reporting competitive results, and the CV focus is using class balanced sampling and the focal loss to improve the classifier training process. And also LDAM is also manipulating the loss, basically assigning large weights to the tail classes and the smaller weights to the head classes during the optimization. So we find our method, although being very simple, is actually achieving much better performance on the overall accuracy. And we also found to learn a good representation, training 90 epochs when you train the backbone is not sufficient. So we actually increased the training epochs from 90 to 200. So we find that the backbone learning is greatly improved by just simply training longer for those risk-next models. And we can actually achieve new state-of-art results by training longer to get a better backbone feature representation, and then you rebalance the classifier to improve the results on the media short and the few short classes. Okay, so I think I have delivered the main message in this talk. I think the take-home message would be the long tail distribution is a really usual phenomenon in the real world. And this is a problem which hasn't been focused on before by the community. While in production, in the real world applications, this is a problem that is very important and the current methods don't really work very well. So we propose when we're solving this problem, we should consider the representation learning and the classifier training separately. And in this talk, we show the representation can be learned by using the instance balance sampling without any tricks. While for achieving good performance in the classifier, we should rebalance classifier and considering the imbalanced class distribution in the data. And our method actually achieve a better trade-off between the head and the tail classes. And we can slightly drop accuracy on the head classes, while more significantly improve results on the head on those tail classes. We have proposed some simple yet effective methods on the classifier retraining. So we suggest the future research could be focusing more on how can we improve the representation quality, which involve a lot more training and computer resources, and which hopefully can improve the representation and consequently improving the overall performance for the long-tailed classification. We have released the code base on the GitHub, and we have more results in the GitHub page. And the results is fully reproducible in PyTorch. So if you are interested in, please scan or click this link and take a look. Thanks for listening to this talk. Hopefully there's some new insights towards long-tailed classification. And next, I'll be happy to take questions offline.
Okay, thanks, Zhicheng, for the great talk.